Hi, this is Professor Fernandez. In this video, we are going to work on Module 3 of Lesson 6. So the topic for the video is interpreting partial derivatives. I've put in here a quick little review of the interpretations of a derivative, single variable, that we know from single variable calculus, and these are the two ones that are used most often. So we know of the derivative f prime of a as the instantaneous rate of change, or just rate of change for short, of y with respect to x. So we're used to this from single variable calculus. And I would call this the rate of change interpretation of the derivative. The second one is what I would call the geometric interpretation. F prime of a is the slope of the line tangent to the graph of y equals f of x at the point a comma f of a. So these are two interpretations that we know from the single variable calculus courses you've taken of the derivative f prime of a. These carry over into the multivariable context. So what I want to show you in this page is how that works, and then on the next page we'll do an example and we'll visualize this. First thing I want to do is show you how the first interpretation carries over. So remember, let's talk about, for example, the partial derivative of f with respect to x. Remember how that was defined. It was in the first module in this lesson, it was the limit as h goes to 0 of the essentially difference quotient as before, except we are now holding y constant since we're talking about a two-variable function. So what I want to do is just rewrite this in a way that's more suggestive of this interpretation carrying over. So what am I going to do? I'm going to say, well, first of all, the h that's changing here is a change in x from literally x to x plus h. So I am going to replace the denominator with delta x, thinking of delta x as the final x value minus the initial one. You can see that there the x's would cancel, gives you h. Second thing I'm going to do is then I'm going to write the numerator in what's going to look like a clunky form, but I think you'll get the point, delta sub x of f. So what I'm pointing out here is that if you look at the numerator, it is a change in the function f, and that's usually, we'd usually denote changes by the symbol delta, but it's only a change in the x direction, right? The y's are staying constant. So it's in that sense that I'm using this new notation, a change in the x direction in f. And then the limit, because we have replaced h with delta x, is limit as delta x goes to 0. Okay, so you can see how this new view of what the partial derivative with respect to x limit definition looks like makes it clear that fx can also be understood as an instantaneous rate of change. We have exactly this conception from the definition itself. This is a rate of change of f with respect to x, but it's instantaneous because we're taking delta x to 0 in the limit. But it's holding y constant, so it's not the same exact type of rate of change up here in the single variable context where there was only one variable. But it's very analogous. So we could have done the exact same thing and replaced or started our analysis in the y direction, and we would have obtained a very similar result with, again, this new notation of delta sub y of f. So this, again, is a rate. This is a change of the function values f per a change of the y values. And then this limit taking is what makes it an instantaneous rate of change. So these notions from single variable calculus of the derivative measuring the instantaneous rate of change, they carry over in this way to the multivariable context. We'll do an example on the next page in a minute. But let me go back and then show you this second one, how this carries over. So recall the picture from Module 1 of the geometry of what's happening here with partial derivatives. So I'm going to go back and redraw that picture. So I had drawn a function that looked kind of something like this, right? And then we had this point AB in the xy plane, and that point had a y value associated with it of AB f of AB. Thinking again of this surface as the graph of z equals f of x, y. And then remember that we said, this point AB has y coordinate b, so that's over here on the y-axis. And y equals b, the line on the xy plane, y equals b, generates this curve that passes through the point AB on the surface. Right? So all of these points on the line y equals AB get mapped up there. So I'm going to get rid of them to not clutter up our diagram here. And then the idea was that this curve itself is the plot of y equals b and x remains constant. So that is now a single variable function of x. And then our idea was, so the partial derivative with respect to x along this curve is like the single variable derivative of the function z of x. We've now restricted it to y equals b. And then the final takeaway from this was that the partial derivative with respect to x at the point AB is like z prime of a. Meaning that if I go back to the point AB, f of AB on the surface, and then I draw the tangent line there, then the slope of that line is this, the partial derivative fx of AB. Okay, so that was the picture we had drawn. That being said, right, you can notice already that I've mentioned a tangent line and I've mentioned a slope. So we are pretty much there to generalizing this notion, this second interpretation of the derivative from the single variable context. It's exactly the same interpretation. So we see here that fx of AB is a slope of a tangent line. This is that black tangent line. The only thing that changes is that we have to be a bit more precise about which tangent line we're talking about. You know, in the single variable context, you drew a function, you picked an x value, and then the tangent line you drew, you know, if the function was differentiable, there was just one tangent line. And that's it. There were no other tangent lines to speak of. Of course, here, you know, on the surface on the left, I could have instead looked at x equals a, and that would have generated this curve, right? And then that generates its own tangent line. So I guess I'll draw that maybe in blue. That's a different tangent line. So that would be the interpretation for the partial derivative with respect to y. That would be giving us information about fy of AB. Nonetheless, the point is that each one of these partial derivatives can still be interpreted as the slope of a tangent line. And somewhat naturally, it's the slope of the line of the tangent line that you obtain by going along the curve generated as this variable changes, and the other one is held constant. Right? In the fx case, that was the original picture here, the red curve that I generated. So there we were holding the y value constant. We were letting x vary. So when we took derivatives here, partial derivatives, we were like finding slopes of tangent lines to that curve. Whereas over here, I would let the y variable vary. So I would be getting a curve like this on the surface that goes up and down in y with x fixed. So once I got to AB and I looked at that tangent line, it would be the slope of that tangent line and be measured by this partial derivative. So it's in this way that these two notions of, two interpretations of what the derivative means in single variable calculus carry over to this multivariable context. Great, so let me go back now to this example and, or I guess, move on to this example. One thing I'm going to change here, I'm going to put a 4 here, so I'll update that. You'll see that update in the printed PDF notes on the website. The reason I'm going to do that is just to make it a little easier for us to interpret and visualize things. Great, so first thing we'll do, find fx of 1, 1 for this function, and then interpret using the two interpretations we just talked about. So the first part I'm going to do is find, and we will interpret. So I'm finding a partial with respect to x at a point. So first thing I'm going to do is find the partial with respect to x at any point. To do that, keeping in mind that this is a 4, it's not going to matter for derivative purposes, but still. So I hold y constant, So this differentiates to 0 with respect to x. The 4 also differentiates to 0, and the negative x squared differentiates to minus 2x. Great, and then from there I substitute in the point 1, 1. There are no y values to substitute in for. X is 1, so I get negative 2. So this is fx at 1, 1. Now, my job for the rest of the video is to help you interpret what this means in the context of this problem using these two interpretations. So let's do the rate of change one first. That is fairly quick. Let's call that A, and then we'll come back and do the geometric, call that B. The rate of change interpretation, so fx 1, 1 equals negative 2. So remember, this is when we were holding y constant, and we were just letting x vary, and considering how, or studying how the function changes as x varies at this point. So we would say that this is the instantaneous rate of change when y is held constant at the point 1, 1. And then I'm going to put in here the y value, so now I do need to go back and remember that I had put 4 here. So f of 1 comma 1 is 4 minus 1 squared, that's 2, at the point 1, 1, 2. Okay. So what does this mean, right? If you relay this to someone else in the class, that would give them a little bit of a picture of what's going on. You know, without telling them the function, you could say, hey, I'm working with this function, and if you go to the point x equals 1, y equals 1, z equals 2, so let's see. I'm trying very hard to draw a little box. There we go. That's the point 1, 1, 2. If you go to that point, the function's instantaneous rate of change in the x direction is negative 2. So that's going to give somebody a lot of information, because the picture that, you know, it takes a while to develop all this intuition, but the picture that might come in their minds is, oh, if I look only in the x direction, if I slice the function to get that curve, if I scroll up here, to get this red curve that varies in x but stays constant in y. If I slice the function that way, then the slope of that curve at that point, you know, this point, is negative 2, meaning that the function is decreasing as I increase x values. So in other words, we expect that the function's values are dropping there, right? Remember, this is increasing x, so this line has negative slope when you look at it with this being increasing x. So this is a nice instantaneous rate of change interpretation. And then this person might even take it a little further, and they might say, oh, so what's the partial derivative there? And you would say, oh, fx of xy is minus 2x. So you could actually, using this instantaneous rate of change, predict the change in the function's values if you moved a little bit further away from this point in the x direction. So what do I mean? Well, we know f of 1, 1 is 2. How about f of, let's say, 1.05 and 1? Right, so moving a little bit away from the point I calculated the instantaneous rate of change at. And just like with normal derivatives, where you can approximate the value of the function using the derivative at the point, we would say, oh, this is approximately the value of the function, which is f of 1, 1, plus the derivative at that point times the change in x. Okay, so this is effectively the linear approximation, the linearization that you learned in single variable calculus. That's actually the topic of the next lesson. So me bringing it up now is a deliberate point to kind of plant the seed and set the stage, but also again to let you know that when you hear rate of change, it really is the quote-unquote y values. It used to be the y values. Now it's the z values changing as a function of some other variable. meaning you can actually approximate the changes in these values using these other notions like the derivative. So anyway, if we kept going here, what would we do? We'd say f of 1, 1 equals 2. Fx of 1, 1 is minus 2. And the change in x is 0.05. Great. So we have 2 minus 10 over 100. 2 minus 0.1, so that's 1.9. It turns out that if you actually calculate f of 1.05 and 1, that is 4 minus 1.05 squared minus 1 squared. It ends up being 1.8975. So that's pretty close, very close actually. And again, it's this notion that if you have this picture in your mind, you're starting at a point, and at that point the function is changing instantaneously by 2 units down for every unit in x. So if I have 0.05 units of change in x, the y values are going to go down by 2 times that change in x. So that's why, effectively we're subtracting here, and we're getting a number that's smaller than 2. The y values have decreased. Negative change, if you will. Great. So that's a quick example of how you not only apply what we just talked about in the previous page, the instantaneous rate of change interpretation in this multivariable context, but then also how you can use it to approximate changes in the function. And again, this is a deliberate planting of the seed for what we will do in the next lesson, which is we'll talk exactly about that. Linearization, linear approximation problem. So part B, let's talk about the geometric interpretation here. So first of all, to do so, let's review. This function is a paraboloid. Why is it a paraboloid? Well, the paraboloids have the property that when you look at slices in the z-axis, they are circles of varying radii. So if I were to draw a contour plot, this is the review part. If I were to draw a contour plot here, when z equals 0, I get x squared plus y squared equals 4. So on the xy plane, I get a circle of radius 4, centered at the origin. And then as I increase the z value, for z equals 2, for example, I get x squared plus y squared equals 2. So I get a circle like that is at z equals 2. And then if I go all the way up to z equals 4, I get x squared plus y squared equals 0. That means I'm at the origin. So if I think of this now in terms of its three-dimensional plot, here's x equals 4, here's my circle, the z-axis, and then here's z equals 4, here's my points, and then they just come down like that, like parabolas. So this is my paraboloid, kind of like a parabolic cap. And we'll see this in the interactive applet in a minute. Okay, so now we have this picture. Now that we have this picture, so let's go back and interpret this in this geometric way. So remember, we're changing x, we're holding y fixed. So this means that if I looked at y equals 1, and I looked on the graph of the function, what would happen? First of all, if I set y equals 1, I get 4 minus x squared minus 1 squared. I get 3 minus x squared. And then that's a function of x. So that's what I'm going to call z of x. It's technically z of x comma 1, because I'm setting y equals 1. So if I look on there, this is a parabola in the xz plane that starts at 3. So 3 is over here. And it opens down. So I'm going to draw that as this kind of black curve here. Okay. It is, this is getting hard to draw, but it is a parabola that it is in the plane y equals 1, right? So that's why it's getting a little hard to draw, and I'll show you with the technology in a minute. But anyway, if you can picture that curve being there, now I get to say, oh, so fx of 1, 1 is, if I go to the point on the function, which again we know is 1, 1, 2, we calculated that up here, and I look at the tangent line to that point, and actually the red dot that I've drawn here is a little less representative of where it should be, because x equals 1 is there. So that dot should kind of be like over here. And I go there and I draw the tangent line, then that slope, that tangent line slope is -2. makes sense again. It's kind of the picture that I drew a few minutes ago. This line is sloping down in terms of the positive x direction. So it's a negatively sloped line in x. And what we're saying up here is that its slope is -2. So that would be the slope of the tangent line interpretation in this context. Let me show you the technology so we can wrap that up. Okay, so first of all, here is the paraboloid itself. Let me turn on my little cursor. So here's the paraboloid itself. I'm just going to pan around so you can see the circular nature of its level curves. In fact, we could generate the level curve here, and there we go. So that is indeed the level curve, and then you can see those circular level curves that are slices. Okay, great. So then I'm going to see if I can turn off this level curve. I always forget how to do this part. Oh, there we go. Great. So here's the function back to the paraboloid. And now what I'm going to do is I'm going to turn on the equation for the parabola that we get from setting y equals 1. So I'm going to do that over here. I've actually found a different way to do it. So I'm going to turn on that curve and see what I'm doing over here. I'm plotting the same function, but only between 1 and 1.05 for y. So you see this is the curve that we just got. This is 3 minus x squared. This is what you would effectively get if you plugged in y equals 1. And then I'm going to change the settings over here so that we can see a little bit more clearly the distinction between those two curves. So I'm going to hide the edges, say constant color, and there we go. So in gray is the paraboloid. In red is the curve z equals 3 minus x squared. You can see, in the xz plane, if I rotate it this way, there we go, you can see here that this is a parabola that starts at 3 and it opens down in the xz plane. Great. So then there's really no easy way for me to plot the tangent line here. But if we were calculating the tangent line at the point 1, 1, 2. So let's go to x equals 1, roughly there, and y equals 1, roughly there. And you can see this is the point at which, in the example, we were calculating the f sub x of 1, 1. And you can see here that if I drew a tangent line, it would be tangent and it would have this slope, which is again sloping down as x increases. So again, there is this nice tangent line interpretation that carries over, as well as the rate of change interpretation. And you can see here that, if we're slightly far away from x equals 1, comma y equals 1, we're in the neighborhood of 2, but not exactly equal to 2. So this also kind of helps to illustrate the rate of change interpretation. And certainly, if I move that way and or that way, the function's values decrease. So again, the rate of change is negative, and that corresponds with what we had done in our work over here. Great, so a very quick little recap of what we did. The two interpretations of the derivative that you know and love from single variable calculus carry over. They carry over in a slightly differently interpreted way. The first one, instantaneous rate of change, this is true, but it's change assuming we hold the other variable constant. Nonetheless, it still gives us the ability to approximate changes in the function. We'll do much more of that in the next lesson. The second notion, slope of the tangent line, that also carries over, but needs to be interpreted in this very specific sense, because now there are a bunch of different tangent lines. These are actually only the partial derivatives in the x and y direction tangent lines. There are other tangent lines that we'll talk about in the next lesson also when we talk about the tangent plane. That being said, I would encourage you to come back to this example and also play around with plotting your own function, so you can move around these curves and surfaces in 3 space and get a sense for how these things fit together. Great, so I'll see you in the next lesson.